Okay, welcome to the fourth example in the chapter of strain. The question reads, a rigid plate is attached to two 10mm by 10mm square bars made of hard rubber with a shear modulus of 1 megapascal. The rigid plate is constrained to move horizontally due to the action of the force F. If the horizontal movement of the plate is 0.5 millimeters, determine the force F assuming uniform shear strain in each bar. Okay, so we start off with givens, and we are given a bunch of lovely stuff in this question, starting with the cross-sectional area of these square rubber bars. So we can easily calculate that because we know that is 10 millimeters by 10 millimeters, and therefore if we multiply the length and width together, we will get the cross-sectional area under shear, right? So it's just 10 millimeters squared, and therefore our cross-sectional area is 100 millimeters squared, right? What other information can we extract? Well, we're given that the displacement of this rigid plate after this force F is 0.5 millimeters horizontally. So if we redraw it kind of like this is exaggerated, and then our structure kind of looks like that, right? This displacement right here is 0.5 millimeters, right? So we can call that delta X. So we can say that, first off, it's a rigid plate, so we're not going to have any deformation or bending or any of that fun stuff. And that its deformation, or its displacement after force F is 0.5 millimeters. Okay, what else are we given? We're given that the rubber bars have a shear modulus of 1 megapascal, right? What is a shear modulus? And it's also called the modulus of rigidity. Yeah, the modulus of rigidity. Well, this relates to a concept which we haven't even gone to yet, I think in the next chapter. Basically, and I think it is, in my opinion, the most important thing you learn in mechanics of materials, and that is the stress-strain diagram. You have the normal stress-strain diagram. This is a quick overview just so you understand the background. And then you'll have the shear stress-strain diagram, right? And the only difference is, instead of normal stress by normal strain, you have shear stress by shear strain, right? On both of these diagrams, you have this linear region in the beginning. On the normal stress-strain diagram, it's called the elastic region, and it's represented by capital E, basically the elastic modulus or Young's modulus, and it is equal to the slope of this linear region, right? The slope of the line. So basically just sigma over epsilon, normal stress over normal strain. Similarly, you have this linear region on your shear stress-strain diagram, and it is defined as G, the modulus of rigidity, or the shear modulus, and it is again equal to the slope, so tau over gamma. So this is the one we're going to use in this question, but this is where this concept stems from, and it really is, in my opinion, and it differs between different materials, and even for future courses, or if you go into I don't know, it's very useful, so I won't get into why and all that, but take my word for it. Okay, so we've established that the modulus of rigidity is equal to tau over gamma. Do I know what tau is? Well, I know the formula for tau. Well, tau is equal to the shear stress, right? And it is equal to the force causing the shear divided by the cross-sectional area under shear. For gamma, it is equal, there's multiple ways to do it, but we're going to deal with the inverse tan of x over y, right? And x in this case would be opposite, and then y would be adjacent, right? And we'll get to it if we need it. But I think that is all for givens. We can move on to unknowns. And obviously we're given these lengths, and that's pretty important. But if we need it, we will reference it. So we can move on to unknowns. Actually, let's put unknowns up here. So unknowns is we want to find the force F. And since we have forces, we are going to do something that we have not done in a while, a beautiful free body diagram, yeah? So let's start with that. Free body diagram. Okay, pretty simple one. You have this bottom plate right here, a top plate right here. Let's say our lovely bar is, I don't know, the rigid bar is over here. And then the other bar, this is the bar, let's call A and B, right? So this is going to be bar B. This is going to be bar A. We're going to have our force F right here. This distance right here is 100 millimeters. This distance right here, 10 millimeters. And this distance right here, 50 millimeters. Perfect. That's a good free body diagram. However, actually, it's not a good free body diagram. Have I done all the forces? That's the question. Let me make this a bit bigger. Have I put all my forces on here? Well, no. I will have, like, it doesn't show it in this diagram, but when I apply this force, is there going to be any reaction force from bar A and bar B? Well, yeah, because if I just apply this force, then obviously, like, it would just leave then, right? Like, what's stopping it? What's constraining it, this rigid plate from just, like, leaving then? Like, what's the point? The thing is, we have two shear forces resisting this motion. Sure, it might deform, but you do have two shear forces. So we can call this VA. We can call this VA. And we can call this VB. So you have two shear forces resisting this force, right? Resisting it from, because if you just had F, then it would literally just pop out, right? So you do have these two shear forces. We can take sum of forces to find an expression to find F, right? And if we say this is positive, we can do sum of forces in the x direction. It's been a long time since we've done this. Is equal to 0. We have F minus VA minus VB. Therefore, we can find an expression for F, and it's just equal to VA plus VB. Right? And this is the key expression we're going to use to find our final answer, our unknown, and that is F. Okay, let's start a new section here. So now we're going to try and find the shear forces. Okay, so I want to find VA, I want to find VB. How the heck do I do that? Well, let's start with VA. Let's start with our variable. And I think it'll be similar for VB. Yeah, it'll be pretty similar. Okay, let's put givens in frame here. Okay, I want to find VA. What is VA equal to? Well, from my formula up here in givens, I can say that VA, or V in just general case, is equal to the shear stress multiplied by cross-sectional area, right? Let me write that down. It's equal to tau multiplied by the cross-sectional area. Do I have the area? Yeah, I do. I calculated it's 100 millimeters squared. Do I have tau? Well, no, not directly, but look at my formula right here. I know that the shear modulus, or the modulus of rigidity, is equal to tau over gamma, right? So I can isolate for tau as gamma multiplied by the modulus of rigidity. For further simplifying, let's write that down. So it's just equal to the shear strain multiplied by the shear modulus multiplied by area. Okay, I still have one unknown. Do I know, or I know the shear modulus, right? I know the cross-sectional area. Do I know gamma? Well, let's look back. Gamma is equal, it's the angle. Let's actually draw a diagram. It'll be much, much better if we draw a diagram. Or should I do it with this? Actually, no, let's draw a diagram. I think that would be much better. Okay, so let me redraw this guy. Okay, so that's basically what our plate looks like right now, right? No, wrong tool. That's basically what our structure looks like right now. I won't add the forces just to not clutter stuff. What is it going to look like when that deflection happens? Well, let's say my bar is over here now. And then this distance, as we said, right here, is 0.5 millimeters, right? Okay. It's going to take the sides with it. It's hugely exaggerated, but bear with me. So that's kind of what our structure looks like now, right? That's kind of what our structure looks like. This is our displacement again, 0.5 millimeters. This is our delta x. right? What do I want to find? I want to find shear strain. What is the shear strain angle in radians? Remember that. What is the shear strain angle I'm looking for? Well, I'm basically looking for this angle right here, right? This angle of deformation, right? This is for, if this is our bar A, this is our bar B, this is strain B, and this is strain A, right? Okay. How can I find them? Well, I can find it using this tangent formula because I know what x and y is. X is simply my opposite, right? And my opposite, if I draw this triangle, and I'm looking for this angle right here, my opposite is this displacement, 0.5 millimeters, and my adjacent is this side right here, and that will basically either be 50 for the top or 100 for the bottom, right? If I draw another triangle right here, if I'm looking for this angle, the bottom one is B, so it's basically going to be tangent inverse of opposite, so 0.5, over adjacent, which for B's case is 100, or it's going to be the exact same thing for A, but instead of 100, it's going to be 50, right? So there, I easily have found my my gamma values. And if you're asking that, this shear strain is negative, whereas this one's positive, we're looking at the magnitude. We don't really care about, because if you realize that it goes into this quadrant, so it's negative, whereas this one goes into this quadrant, so it's positive, it doesn't really matter. We're just looking for the number, the magnitude. So yeah, therefore, I know what my shear strain is, right? And let's just quickly write that down. So if this is my angle that I'm looking for, this is gamma B, this is gamma A. I know that gamma A is equal to the inverse tangent. Just want to check just in case. Yep, it's equal to the inverse tangent, opposite over adjacent, 0.5 millimeters. I won't even include the units. 0.5 over 50. And this one is equal to the inverse tangent function of 0.5 over 100. Right? So those are my two values. Okay, perfect. Do I know shear strain? You better hope so. We just spent time on it. Do I know the shear modulus? Well, yeah, I do know it. It's 1 megapascal. Remember from Givens? It's 1 megapascal for both bars. Do I know the cross-sectional area? Yeah, I do know it for both bars. Do I know gamma? Yes, I do, but it's different for A and it's different for B, right? So basically, the only altercation the only thing I need to add to this formula is differentiating between gamma A and gamma B. So is equal to gamma B, like that. Okay, we can plug in our numbers. See, what did we need in the beginning? We needed to find this force F. How did we how did we come up with an equation to basically find force F? We did sum of forces, and we found that force F is basically just equal to the shear force of A and the shear force or the shear force on the rigid plate by the bar A, and the same thing for bar B. I'm not going to repeat that. And how do we find those? Well, we simply find it using this lovely equation right here, and we have all the values. So we can just plug all that fun stuff in, yeah? VA will end up equaling, I'll just write this down, tangent inverse of 0.5 over 50. Please remember that to use radians, so we get that our shear force from A is equal to 1 Newton, and we get that our shear force from B is equal to 0.5 newtons. If we plug these two values into the formula we have derived for F, we will end up getting that F is equal to 1.5 newtons. Right? Perfect stuff. So that is your final answer.